So you noticed on your exam, you have two problems on Laplace transforms that you could actually solve by other methods. But now I want to talk about solving Laplace transforms where we have piecewise continuous functions. In other words, where the first derivative is discontinuous, right? Here, the first derivative is zero, then it becomes infinite, then it becomes zero again, right? So the first derivative is discontinuous. So Laplace transforms allows us to deal with problems like this, and you could guess that when you're dealing with control theory and electrical engineering, where you have pulse widths and different types of you can have a ramp input or you have sawtooths. When you do digital signal analysis, Laplace transforms becomes very important. Laplace transforms is also used to solve partial differential equations, where if you have two variables of a partial differential equation, you could use Laplace transforms to eliminate one of the variables, and then you solve for the other. So it is a very useful method, but we're not doing any partial differential equations in this class. All right. So let me start talking now about the first thing I want to talk about is the unit step function. I was going to write this stuff out, but when I get into problems, we'll do that. Okay. So the unit step function, I can define the unit step function. This here is 1, right? This is 1. And so here's my unit step function. So I define the unit step function to be t minus a, and the definition is that when t is greater than 0 but less than a, greater than or equal to 0 and less than a, it's 0, right? The function is 0. And then when t is greater than or equal to a, right, then the function becomes 1. Now your book uses a much fancier script than you here. When I did all these charts using an application called MatType, and they didn't have the fancy U that your book uses, so I just made a U there. Some books will also use an H, but it's also called the Heaviside step function. So some books use an H. Okay, so so for example, if I wanted to have a unit step function that was 2 units, right, I would just write it like this. This would just be 2 units and just multiply by 2. All right. Now, one of the things about the unit step function, it allows us to construct very complicated, much more complicated functions. In other words, it allows us to turn functions on and off. So, for example, let's say I have a very simple function here that's equal to 2t, right? This function is equal to 2t. And I can use the unit step function to turn it on and turn it off. In other words, if I write it like this, right? When this is going to be 0, right? This is going to be 0. I'm going to be multiplying 2t times 0 until t becomes minus 2. Excuse me, until t becomes 2. Then once t becomes 2, it turns on, and then I'm getting the function 2t. And then if I now now this is 0, right? This is 0 until t becomes 3, right? When t becomes 3, this is going to become 1, and then I'm subtracting, right? So this is so then I'm subtracting this from this, so then I'm getting 0 again. So the function, I can have a function here that I could turn on at time t equals 2, and I can turn it off at times t equals 3, just using this relationship here. Okay, so there's a general form. There's a very general form of turning a function on and off, right? Where I could use this relationship here, right? You see this here? So I have some function g of t, and I want to turn it on at time t equals a, and I want to shut it off at time t equals b, right? So I could just use this relationship here, right? Because this will be 1, right? As soon as this is both of these is 0, right? Until t becomes a. When t becomes a, then this becomes 1. So I'm getting the g of t times 1. And then when t becomes b, right, this is becoming 1, and I'm getting 1 minus 1, which is 0, so it's shutting it off. Okay, so here's an example. Let's say I wanted to model a pulse that looked like this. Okay, so the way I can model a pulse is like this. I just put the 2 in front of here, right? I put the 2 in front of here, and this is gonna turn on, right, when t is equal to 2. So when t is equal to 2, it pops up here. All right, and then what happens is then now when t is equal to 4, right, this becomes -1, so it subtracts from this and it drops back down. So this is how I can model a unit step function using the this would be using the unit impulse, right? So once again, we call this the we're calling this the unit step function. I guess, yeah, we call that the unit step function. And here I'm just calling this a pulse. Okay. All right, so here's a more complicated example, right? If I wanted to model something that looks like this, right? Let's say I wanted to model something that looks like this, then what? So let's see. So it starts out at 2, right? It starts out at 2, and then I wanted to jump down to -1. So I put 3 u t, right? So this is going to turn on at -1. So I'm going to be subtracting 3, right? So now I'm down here. And then let's say I want to add 1, right? I want to add 1 at t equals 2. So then it adds 1 from here. All right. So if I had something that looked like this, right, I can model this using the unit step function. Okay. Now I'm not going to be, if anything, you'll be getting solving a differential equation that has something like this. You won't be getting a differential equation of something like this. Okay. Let's see. All right. All right. So what I want to do now, maybe now I'll go to writing stuff out. Okay. So let's see. Let me. So obviously we need the Laplace transform for the unit step function, right? I don't know if your book has it. So let's come up with the Laplace transform. Now, what's important? You don't need to understand the derivation of the Laplace transform for the unit step function, but you have to understand how to use it. Okay, you have to understand how to use the result when we solve a differential equation. All right. So let's see. So we have this unit step function, and this is equal to 0. I guess I should put on where's my glasses? I always get worse and worse. Okay. So here's our definition of the Laplace transform, right? It's now I'm putting the u in here. It's fancy u. Then this is t minus a, right? dt. Now, what's happening here is, well, I guess let me put in the limits of integration. I mean, let me put in the fact that it's it's an indefinite integral. So we got the limit as b goes to infinity of 0 to b, and this is equal to e to the minus st, and then u of t minus a dt. Okay, so all right. So now what's happening here? Well, this here, when this is 0, in other words, I can write this as the limit as b goes to infinity. All right, well, I was skipping a step. Let me do it like this. I'm going to break it up into 0 to a, break it up to 0 to a, and we're going to write this as e to the minus at, e to the st, and times 0 dt, right? In other words, when I go from 0 to a, this is 0, right? This function is 0. From 0 to a, so I'm multiplying this by 0. So this whole thing, I was going to leave this step out, but so this whole thing is 0, right? And then now I have plus the limit right, as b goes to infinity of the integral from a to b, right, of e to the minus st dt. Okay, so now I got the limit as a goes to right. So this is just one now, right? So in other words, from 0 to a, this is 0, but from a to b, this is 1, right? So this is 1, right? So what do I have now? So now I just have to do this integral, right? So this integral is going to be the limit as b goes to infinity. And let's see, this integral is going to be e to the minus sb. Well, yeah, e to the minus sb divided by, well, I guess I'll do it. Once again, I was going to skip a step, but I see in my notes I didn't. So this is going to be e to the minus st, and I got a minus sign divided by s, right? And this is evaluated from a. It's going to be evaluated from a to b, right? It's evaluated from a to b. So so what happens when b goes to infinity, right? The first thing becomes 0, right? When b goes to infinity, this becomes 0. So the first term is 0, right? So this is equal to 0, right? Everybody see this is 0. And then I'm getting a minus e to the minus sa divided by s, which is equal to e to the minus sa divided by s. Okay, so therefore, what we need to know is that the Laplace transform for the unit step function, right? I'm using this curly Q for the unit step function, is equal to just e to the minus sa divided by s. And sometimes you put the a first. Most of the time you put the a first. Not that it really matters. So we can also write it as minus as. Okay, in most books it's written that way. Okay, so that's the Laplace transform of the unit step function. Now let's see. Right, so now let's say that we did have our complicated one. We had this here. Okay, this is, let's just find the Laplace transform of this thing. This is pretty straightforward, right? So far, so good. Okay, so let me find the Laplace transform of this, right? So Laplace transform of 2, right? The Laplace transform of 2 is just going to be 2 over s, right? Remember that? The Laplace transform of 1 was just 1 over s. So the Laplace transform of 2 is just 2 over s, right? So, all right. So down here, I'm doing the Laplace transform, okay? So this one here, this is going to be minus, I'm going to have the 3, right? But now what's the Laplace transform of this? Well, Laplace transform of this is going to be an s, right? And then it's going to be a e to the minus a is equal to 1, so just be s. Okay. And then the Laplace transform of this is just going to be e to the 2, be 2s, right? So far so good over s, right? Because, right, this is here the signs match. Sometimes you got to be careful if the signs are different. So all right, so this is my Laplace transform of this thing, right? So this is the Laplace transform of this. All right, I guess I should have put the L here. But you understand? Okay. All right, so getting the Laplace transform of the unit function is not that difficult, but where sometimes the difficulty comes in, especially when we have to find the inverse, is when we have to do the, see, many times.
Oh, excuse me, Professor. Can you go back to the previous page really quick?
Sure.
Sorry, I wasn't done copying it down.
This one, this here?
Yeah. Oh, may I also have permission to record this session as well?
I think I'm talking to Connor, right? I recognize your voice. Okay. You should have permission to record.
Oh, no, it's Calvin talking.
Oh, okay, sorry. I guess I didn't recognize your voice. Let's see, where are you? Oh, okay, it's up here. Okay. All right. So it normally puts them in alphabetical order, but now yours went to the top. It's not in alphabetical order. Okay, anyway. All right. Okay. Other questions? All right, so let me move on now. Let's see, what do I want to do now? Okay, now we also need to know the Laplace transform of when I multiply it by a function. Okay. Let me just okay, so in other words, I need to know the Laplace transform of when I multiply the unit step function by a function. Okay, so let's see, how do I, so let's use the definition to solve this. This is going to go from 0 to infinity. I don't think your book has this. I don't think your book has this definition. They don't prove this. Okay, I'm just putting in the function, okay, dt. All right. So now, once again here, this is going to be 0, right? So in other words, I could break this up, break up the integral from 0 to a, right? And that integral is going to be the minus sign here, right? So that integral is going to be 0, right? This would be 0, right? dt. And then that's going to be equal to, let's see, this would be the integral now from a to infinity, right? The integral from a to infinity. And now this is just 1, right? This is, I'm sorry. You understand what I'm doing here? This is from 0. I think it's a little bit different in my notes. This is from 0 to a, but it's the same thing. 0 to a, you know, this is 0. So, and then from a to infinity, right? Because I got the a here, this is 1. Okay. All right, so now let's see. So now I have this, all right? So I wanted to get the Laplace transform, we really need to start from 0, right? So I want this, I want to shift, I want to make a change of variables with my t such that I start this at 0, all right? So I'm going to say that that t is equal to w plus a, right? So then dw, dt is equal to dw, right? dt is equal to dw. So so when that's true, well, let's see. So so w then is equal to t minus a. Well, so the thing is that when t is equal to a, right, w is equal to 0, which is what I want. So now when I make that change of variable, now I start from 0. So I go from 0 and I still go to infinity, right? Infinity is not going to change, right? So I still go to infinity. So I'm going to have now e to the minus s. Now remember, my t, I'm writing as w plus a, right? Writing w plus a. And then my f is w plus a, right? Because I'm substituting in place of t, I'm putting in w plus a. And then this is dw. Okay. All right. So so let's see. So I could take the e to, I could remember now I'm integrating with respect to w, not with respect to s. So I could take out this e to the minus sa, right, out of the integral. I can write this as the integral from 0 to infinity of e to the minus sw, right? And then times, okay, and then this is the same. Okay. And now what? Well, this here, right? This here now is just the, let me write it like this. No, okay. I guess the way I did it in my notes. So now W, it's just a dummy variable, right? So I can go back to T because we want things in terms of T. So I'm just gonna go back to T. Right? So all I did is I just went back from T to W. So now we can recognize what this is, right? Okay, so this is the Laplace transform. This thing here, right? This thing here is the Laplace transform of f of t plus a, right? That's what this is, right? This is our, right? We go back to the basic definition of Laplace transform. So this is the Laplace transform of the function t plus a. But then I also got this e to the minus sa, right? So finally, the important formula, let me write it here, is that the Laplace transform of the unit of a function times the unit step function, right, is equal to e to the minus sa times the Laplace transform of the function of t plus a. So we have to shift the, whatever our function is, when we multiply by the unit step function, we want the Laplace transform of a function times the unit step function. We have to multiply by e to the minus sa, and then we have to take the Laplace transform of the function and shift it by a. That's what we just proved. Okay. Okay, so that's good. But what's important now, if you're following along on chart 20, so here's, let me just copy these down. That the Laplace transform, this is what we need to know. The Laplace transform of the unit step function is equal to, right? And then the Laplace transform of the unit of, when we have a function times the unit step function, that's equal to e to the as, and then it's the Laplace transform of f t plus a. Okay, and now we also need to know the inverse transform. Right, the inverse, you just take the inverse of this. I guess I didn't really prove the inverse. Okay, so this is the inverse Laplace transform of this. Okay. All right, we'll see how to use this. And then the inverse Laplace transform of this here. This is just equal to the unit step function. Okay, so when you see this, when you want, this is going to be important, but when you we'll see, like when we do the Dirac delta function, we'll end up getting the unit step function as part of your solution. So when you see this, okay, when you see a form that looks like this, and we take the inverse Laplace transform, you know you can have the unit step function, okay, in your final answer. Okay, all right. So this is, let me just make sure I got these right. So these are the important Laplace transforms and the inverse Laplace transforms for the unit step function, and then when we multiply by a function. Let's see. Okay, and these are in my notes. Okay, they're much neater in my notes. Okay, all right. All right, so now how do we use this? So let's see. What is the Laplace transform of t and then multiplied by the unit step function? Okay, All right. Well, first of all, I'm going to use this. I have to use this relationship here, right? I got to use this here. So if I look at this, so first of all, I'm going to have it. Did I leave out a minus? It left out a minus. Yeah. Okay. Yeah, because I know I have to have a minus sign here. Okay. So this is going to be minus, right? Minus 2s, right? It's minus 2s. I got this 2 here, right? And then it's going to be t. Let me not skip a step. It's going to be the Laplace transform of t, which but it's going to be t plus a in this case, right? It's going to be t plus a, right? I got to add the a, right? It's going to be t plus a. So now I have to take the Laplace transform of this. Okay. So so this is e to the minus sa. Now the Laplace transform of t, that's going to be 1 over s squared, right? Right. Remember, you have the yeah, it's like this is 1 over s squared. I hope everybody knows that. So this is going to be 1 over s squared, and the plus transform of a is just going to be well, I don't want to. It is a, but in this case here, our a is what? Our a is 2, right? It is a, but the a is 2. Okay. Right? So our a is 2. So this is now 2. The plus transform of 2 is 2 over s, right? Remember, the plus transform of 1 is 1 over s, and then it's just so that's it. So the plus transform of t, the unit step function, is equal to, in this case here, it's equal to e to the minus 2s, and then it's 1 plus s squared plus 2 over s. Okay. All right. I want you to try one. Without looking at my notes, try to do the Laplace transform of the cosine of t times the unit step function of t minus pi. Okay. What does this come out to be? Let me give you a minute to do that. Let me, am I going off the page here? Okay, so let me go ahead and do this. So we want to find the Laplace transform of this, right? So first of all, this is the relationship we're going to use. This is the property that we're going to use. Okay. So so let's see. So here I got a pi, right? Here I got a pi. So this is, I'm going to write this when I want to find the Laplace transform of this. This is going to be e to the minus pi s, right? And then it's going to be the Laplace transform of cosine of t plus pi, right? And let's see. And so this is e to the minus. Now the cosine of plus pi. Let me that's equal to minus the cosine of t, right? I can write it like that, right? This is equal to minus the cosine of t. So then this is going to, now what's the Laplace transform of cosine? So this is going to be, there's a minus sign here. Now cosine, you know, cosine is s, and in this case it's s squared plus 1, right? So here we have it. This is the Laplace transform of this here. Okay. Remember now, cosine of t. Well, cosine of k. Let me make the cosine of k. Cosine of kt. Cosine of kt. The Laplace transform of cosine of kt is equal to s over s squared plus k squared. Right. So here k is equal to 1. Okay. All right. Any questions? Now, what becomes more difficult is the inverse. All right. So let me give you a second. See if you could use the property for inverses, and come up now with the Laplace transform of this thing. Okay, see if you can come up with the Laplace transform of this. And so the property you want to use this property here. We want to use that. Okay. We want to use this. So you need to know what this thing is, right? You need to know what this thing is. Where students sometimes they forget to multiply by the unit step function. All right, so let me give you a minute to try to figure this out. I keep forgetting to. On the next exam, you'll have one problem where you have three problems. Yeah, there'll be a part A, B, and C where you have to find the Laplace transform. So I'm going to give you something where you have to find the Laplace transform, and then you're going to have three problems A, B, and C where you have to find the inverse Laplace transform. So that's two problems. Okay. So you have a problem where you have to find three Laplace transforms. You have a problem where you have to find three inverse Laplace transforms. And let's see. And then there's going to be a problem on using the solving the differential equation with the unit step function, which we're going to be doing shortly, and also solving a differential equation with the Dirac delta function. And then there'll be a problem on one problem on a system of differential equations. So that'll be the last exam. Okay. All right, making good progress today. All right, so well, first of all, you need to recognize that this thing here is cosine, right? This is cosine, but it's cosine, right? It's cosine, right? This thing is cosine. It's cosine of if I just forget about this, right? This is cosine of 2t, right? But now my t is shifted, right? My t is shifted here. So so the result here, this is going to be, well, I'm going to have this thing here, right? So this is going to be, my answer is going to be the cosine of 2. Now the t is become t minus pi over 3, right? And then because of this, I'm going to have the unit step function, right? That's what I'm doing here, right? I'm following this rule right here. This here, in this case here, it's cosine, right? This is the cosine, right? So that's the cosine. But now I got to remember that my function, though, this is the cosine. But when I take the cosine, I have to shift the t by a, right? And my a in this case is pi over 3, right? So this is pi over 3. And then I got to multiply it by the unit step function, okay? So, so I want to make sure you understand that we're going to do some more problems too. That the inverse Laplace transform of e to the minus pi over 3s, and then this was times s, right? This turns out to be cosine of 2, right? Now it's t minus pi over 3, and then times the unit step function, which is t minus pi over 3, right? We're using, let's see. We're using, right. These are the important ones right here, okay? Okay, so that's what we did. In this case here, we use this here, right? And, okay. You notice too that if this is 1, right? If this is 1, you get this, right? If we're just dealing with 1. Okay. So this is actually more general than this. All right, let's okay, I want you to try another one. Let's see, this one here is gonna, it's got another step that the other one didn't have. See if you can do this. Now this one here, you also have to use the, in addition to the unit step function, you also have to use the axis theorem, right? Remember the S, the theorem that we talked about yesterday. You have to use both. So I'm going to try to break this down for you, but I want you to try it first. Yeah, so in this problem here, you're also going to need this. I'm actually going to give you the answer, then I'll work it out. Let's see if you get this answer. That's the answer. So let's see how we figure this out. So see if you get, if you get the answer, why don't you put it in chat? Let me know. Be able to figure it out. This is about as hard as it gets as far as, well, when you get this far anyway. Sometimes you need to, oh, I'm missing a 2 here. Yeah. No, I'm not missing a 2. That's later on. This is what we're starting with. Just to make sure. Yeah. So you may get a problem like this on the next exam. I'll be back in a second. Okay. All right, let me get started. I'm gonna break this down. Let me show you how I'm gonna do it. There's more than one way of doing this. But and this is kind of like what I have mine up. Remember now, the Laplace transform, well, I'm sorry, the inverse Laplace transform of we all know that this is a sine of 2t, right? Hopefully that everybody knows that this is the sine of 2t. Now, I have that here, right? But I also have this as being shifted, and I don't have the 2, right? I don't have the 2 here, right? So, so in other words, I could say that this is 1/2. Let me do this now. This is the way I kind of worked it out in my notes. I can write 1/2, right? And 1/2 so this would be 1/2 sine of 2t, right? So you see here, I got this. You see, I have to use the other theorem that we learned about, that I got the shift to 2. Okay, so so what's going on here is that in addition to this, right? Remember now, everybody agrees, right, that you know, this is 1/2, right? That this is the 1/2 sine of t. But remember now, if I have this now, suppose now I have this. That's plus 2. Okay, now I have this, right? So when I have this, that's going to make this, it's going to give me this E, right? It's gonna give me an E to the minus T, minus 2T, right? You follow me? Remember from the theorem, the parallax, not the parallax theorem, the S translation theorem that we did on, guess we did that on yesterday, right? So that's giving me this times the sine. I got to put it in one here, times the sine, right? So, so I want you to recognize first that if I have this, right, it's going to be 1/2 the sine of 2t. Now, I have this additional shift, right? Remember, we learned yesterday that that we have this. I gotta multiply by the e to the minus 2t, right? So I got this now. But now I also have this e to the minus pi divided by 3s. So that's going to shift everything. That's going to take all my t's and shift them, and then I got to multiply by the unit step function. So the end result of this thing, I hope you can see this. So the end result of this, right? I have this, right? So this t, I got to shift this t minus pi over 3, right? I got to shift this t minus pi over 3, and then I got to multiply by the unit step function, which is t minus pi over 3. So this is the answer. Is that making sense? Okay. This is what this seems to be the thing that students have the most problem with. Try another one, okay? But really, try to do this. Like, well, first, before I go, does anyone have any questions?
I have a question.
Yes.
Since you multiply by 1/2, shouldn't it be a 2 inside the Laplace transform?
No, no. I need a 2 here, right? There is no 2 here, right? There is no 2 here. This what the Laplace transform of sine, right? The inverse Laplace transform of sine. This is k over s squared plus k squared, right? So this is the sine of kt. I don't have a k. I don't have a 2 here, right? There's no 2 here. So I had to right, in order to get yeah, okay. Oh, are you saying I should have a 2 here?
Yeah.
Yeah, you're right. You're right. Okay. The answer, everything's right. The answer's right. Good. Any other questions? Someone got it. Okay, so I want you to try another one now. Try this one. Let's see, so the answer here is gonna be 2t minus 2 squared. That's what the answer turns out to be. Okay, so let me go ahead and do this one. Remember now, the inverse Laplace transform of, there's another form for this too. This is equal to, you know, this will be t to the n, right? So, so in this case, if I just look at this s cubed, right? Have this the s cubed. So that's going to be, right, if I just want the inverse Laplace transform of that, s cubed. Okay. So there's going to be 2 factorial here. Let's see. Yeah, this will be n is equal to 2, so it's 2 factorial. And then this is going to be t squared, right? So that's t squared. All right, that's t squared. I got a 4 here. I only have a t2 here, right? So I'm going to take out, I'm going to do it this way. I think it's a little bit different in my notes. I'll write the 2 here. And then divide this by s cubed. Okay. So now this here is my t squared, right? This is my t squared. So I got a 2 t squared. But now that's if I don't have this thing, right? So I have this thing. So my t squared, I have to shift my t. My t, I have to write as t minus pi over 2 squared, right? Minus pi over 2 squared, and then times the unit step function, which is t minus pi over 2. Okay, so that's what I have up here. Okay. Okay, so I think I get those 2. All right, so now let's solve a differential equation. So this is kind of like what you can expect on the test. So let's see. Sine t. Okay. All right, and this is okay. So let's go ahead and do this. So the first thing, we take the Laplace transform of everything, right? I'll write it out like this. You take the Laplace transform of this. Okay. All right. Now, what is we should all know now with the second derivative, you have this on the test. What's the Laplace transform of that, right? Well, that's going to be s, right? I'm just doing the Laplace transform of this. It is going to be s squared, big Y of s. Remember, we have to solve for s, and then minus, let's see, this is 0, right? This is 1. Okay, so it's going to be minus s, right? Is it okay? Does everyone agree with me that this is s here? Because this is going to be a y0 times s, but y0 is equal to 1, right? Then I got minus y prime, which is 0. So this is 0. right? Okay, so now I'm going to take the Laplace transform of this, and this is going to be 4. This is going to be 4, right? Okay, so that's what I have on this side of the equation. Everything looks good. All right. So now what about here? Now I got to take the Laplace transform of this. Okay. So we know now that the our rule is that this is going to be e, right, to the minus 2 pi s, and then yeah, it's going to be e minus to the 2 pi s, and then it's going to be the, let me not skip a step. Then it's going to be the Laplace transform of the sine of t plus 2 pi. Now this time they made this, in this problem, it's actually, pretty simple. The sine of t plus 2 pi is also sine of t. So I can write this as e to the minus 2 pi s, and then the Laplace transform of the sine of t, right? So then this is e to the minus 2 pi s, and then the Laplace transform of t, right? This is just going to become a 1 over s squared plus 1, right? Remember the Laplace transform of sine, right? Everyone remembers the Laplace transform of sine. If not, you just look it up in the table. All right, so let's see now. Okay, so on this side of the equation, I could factor out, let's see. I want to solve, right? We have to solve for this. We have to solve for this. So we get y of s. It is going to be s squared plus 4. It's all equal to this. And I'm going to bring this minus s, I'm going to bring over to here, right? Okay. So here's what I got now. I got y of s is equal to e to the minus 2 pi s. And then I got s squared plus 1. I got s squared plus 4 plus s over s squared plus 4. Okay. All right. Now what do we do? Okay. I'm not gonna. If you take a look at this, this is gonna end up being. You should be able to see that this is gonna end up being what? End up being cosine. Let's see something. Yeah, right. I hope you can recognize this is easy. This is just cosine. When I take the inverse of this, I'm just going to get cosine. So I just need to look at this. This is what I need to investigate. So how do you think we do this? Well, let's see. So what I'm going to do is I'm not going to worry about this, right? You don't need to worry. We'll deal with that. We could deal with that. So what we're going to do though is we're going to break this up. I'm going to break this up into partial fractions. I can do it this way. Okay, that's good. All right, so I'm breaking this up into partial fractions using partial fraction decomposition. By the way, there's also another method, and sometimes it's easier, sometimes it's harder. It's called convolution, where you end up, instead of doing partial fractions, you end up doing integrals. It's in my notes. I have it on Blackboard for the student that's interested. On instead of using partial fractions when you deal with Laplace transforms, there's a method called convolution that you can also use. Okay, so All right, so now we have to solve for A and B, right? So let's see. So yeah, let me just do it like this now. Let's solve for A and B. So let's see, it's gonna be 1 is equal to A, and then this is gonna be S squared plus 1 plus B, which is S squared plus 4. Okay, so let's see, let me write this out. So I'm getting that, let's see, this is telling me, let me not put the 1 here. There's no S squared on this side of the equation, right? So this is telling me that that A plus B is equal to 0, right? A plus B is equal to 0. There's no S squared here, right? Here I got an A S squared, here I got a B S squared. It's also telling me that 1 is equal to A plus 4B, right? It's also telling me that 1 is equal to A plus 4B. So A is equal to minus B, right? So this is telling me that 1 is equal to minus B plus 4A, 4B. There's more than one way of doing this, but 4B. So let's see. So this is telling me that, yeah, so, okay. So B, this is 1. B is going to be, this is 3B. Okay. So B is equal to 1/3, right? B is equal to 1/3, and A is equal to minus 1/3, right? A's got to be minus 1/3. Okay. All right. So now what? So now I want to. Well, let me put this up here. I had this up here, so I could show you this all at once. Just copy this over. Okay. So so this is what I have now. So now let's see. So now I'm gonna have y of s. Let's see. I'll have the y of s is gonna be equal to let's see. Oh, it's the 1/3, right? The 1/3. It's gonna be equal to e to the minus pi. And then it's which one is a is has a is that, right? So that's gonna be minus, okay. Make sure I put the 1/3 with this here. So this is gonna be 3 down here, and this is gonna be s squared plus 4, right? And then I'm gonna have a plus e, and then this is gonna be 1/3, and this is s squared plus 1, and then plus, there's a minus sign here. And then I got this thing here. Okay, let's see if that's right. Okay, all right, good. All right, so now we want to take the inverse Laplace transform of both sides, right? So when I take the inverse Laplace transform of this thing, like this is just, right? Take the inverse Laplace transform of this. Now let's see. When I take the inverse Laplace transform of this, right? Let's see. This is if I had a 2 up here, right? If I had a 2 up here, this would be sine, right? In other words, if I put a 2 here, right, then this thing here would give me sine. I can't just put a 2 up here, so I'm gonna divide everything through by 2. We do it this way. This one here, okay, if I had a 1 up here is good. Yeah, if I have a 1 up here, which is what I do have, then this would be sine. Okay, so does everybody see? I put a 2 up here and I put a 2 down here. So this here now, well, let me do it this way. I'll give myself some room. I'll write this as the sine of 2t. All right, you do it like that. Sine of 2t. divided by 6, right? Because this is the sign here. And now I got a t here, but I have to shift my t. Oh, and there's a minus sign here. Let me. Right. Okay, so I got this minus sign, and I divided by 6, right? Minus sign. And okay, so now I took care of that. Now I have the sign of 2t, but my t now is going to be t minus 2 pi. Okay, and then the other one is going to be this is going to be 1/3, right? Here 1/3, right here. And then this is going to be the sine of t, right? Sine of t minus 2 pi. And then everything, all of this here, everything here, the whole thing is going to be multiplied by the unit. Well, each one of these terms are multiplied by the unit step function, which is t minus 2 pi. Okay. And then this term here is easy, right? This term turns out to be the cosine of 2t. Okay. All right. Now, in this case here, you can actually, oh, you can leave it like that. It's fine. I think that's what's in my notes. Let's check my notes. Make sure I got the right answer. Okay, could you see both? Okay, so here's what I got my note. I got the cosine here. All right, so it's 1/3. Okay, and then the minus 1. Okay. All right, so my notes, I guess I did things in a little different order. Okay, any questions? Where are we on time? Okay. All right, well, we could, I think you'll find the direct delta function easier. So this is the unit step function, and this was a differential equation. And we'll do more problems. I'm actually, yeah, tomorrow we'll do more problems. But I guess let's start on the direct delta function. But I'll take any questions before I start on the direct delta function. Okay, no questions. It's called a function, but I believe mathematicians really don't consider it to be like the definition of a function. You know, Dirac was one of the founders of quantum mechanics, and it turned out in quantum mechanics, the Dirac delta function becomes very important. Okay. All right. So, before I talk about the Dirac delta function, I just want to talk about the unit impulse function, because what's going to happen is we're going to take the unit impulse function and shrink it down to a width of 0. We're going to let the width go to 0 and the height go to infinity, and that's basically the Dirac delta function. So, let's see. You're able to see. Let's see. So let me use because my pictures are better than, I don't want to spend time doing the drawing. Okay. So if we have a unit impulse function, in other words, I can define a unit impulse function where I'm using the subscript a to represent the unit impulse function. When I let a go to 0, this is going to disappear. You'll see what I mean in a minute. So the unit impulse function is going to be defined where it's 0, right? It's 0 until t0 minus a. Okay. So in other words, here it is right here. Here's a picture right here. So it's 0, and then when I get to T0 minus A, here's T0, right? So this pulse, right, is the length of 2A, right? The pulse is the length of 2A. And this is the time T equals 0. So, okay. So it turns on at T0 minus A, and it's off at T0 plus A, right? And the height here is 1 over 2A. All right. So you follow that? So I just have an area here, right? I got the area here is just 2 times A, right? Times 1 over 2 times A. In other words, the area is 1. Okay, the area is 1. I make this 2A, I make this width 2A, and I make the height 1 over 2A, right? So the area is just 1. All right. Now, if I take smaller and smaller values of A, the area still remains as 1 unit, right? In other words, I tried to draw this, you know, where the area is the same. In other words, this area is the same as this area, same as this area, same as this area. But what we're doing here is we're taking smaller and smaller areas of A, right? In other words, A is becoming smaller and smaller, right? So this is shrinking, and then this is going higher, right? When A becomes smaller, this becomes larger, right? When the A here becomes small, this is becoming large. And when the A here becomes small, this is becoming small. So this is becoming large, but the ratio, right? No matter what my A is, the ratio is always 1. Okay, that makes sense. There's other ways. There's actually, if you ever take a course in quantum mechanics, they actually define this is the way your book defines the Dirac delta function. But some books will actually take a Gaussian distribution and then shrink the Gaussian distribution. That's the way they do it in quantum mechanics. It's the same thing. Okay. So anyway, so what happens? Now I'm trying to give you a pictorial of what the Dirac delta function is all about. So if I take the limit as A goes to 0, right? What I get is I get a spike. All right. And we get a spike of 0 width. It's kind of weird, right? We get a spike of 0 width and an infinite height. So this is a spike of infinite height, 0 width with area A. Okay. So it's got area A, 0 width, and infinite height, because the area is excuse me, not area A, area 1, right? The area is 1, right? But the spike is infinite and the width is 0. Because what we're doing is we're taking this thing and we keep, you know, shrinking the A, so it gets narrower this way and it gets higher this way. So eventually it approaches infinity this way and 0 this way. So you get this infinite spike. All right. So that's the idea behind the Dirac delta function. Okay, so now see, where are we? Okay, so now some important properties of the Dirac delta function. You can see when you look here, right? So here's the property of the Dirac delta function, is that it's infinite when t is equal to t0. The Dirac delta function is infinite, and it's 0 every place else. So that's our definition. Dirac delta function has an infinite spike, right, and 0 width in area A at t0, right? And every place else it's 0. Okay, every place else it's 0. And okay, so that's one property of the Dirac delta function. Another property is that, okay, if I do this integral from 0 to infinity, that's going to be 1, right? The integral from 0 to infinity is 1, right? Because this area is 1, even though the spike is infinite and the width is 0. Another property of the Dirac delta function is that if I take the Dirac delta function, if I do an integral of the Dirac delta function times the function, it's just equal to the function evaluated at this point. Okay. So from this property, your book doesn't do this. So from this property of the Dirac delta function, okay, we can get what the Laplace transform is. Okay, so let me actually do that. So I have this property of the Dirac delta function. Right, and our definition of a Laplace transform to any function okay. So so from this property here, right? From this property here, okay. So all right, so this is my Dirac delta function is, we said this is the Dirac delta function. And we use the symbol delta. So if I put that in here, right? This is my definition of the Dirac delta function. I stick it in here. That if I use this property of the Dirac delta function, then this is just telling me that what is this integral? Well, this integral is just e to the minus s t0, right? I'm using this property here. So the Laplace transform of the Dirac delta function okay, let me do that one. Plus transform of the Dirac delta function is just equal to e to the minus s t0. And normally we've been using a, so let's see. So I can say now the Laplace transform of the Dirac delta function is just equal to e to the s a, right? So now we have the Laplace transform of the Dirac delta function, and that's what we need to know. All right, if you understand this, great. But this is what we need to know, the Laplace transform of the Dirac delta function. Okay, let's see now. Do I got time to solve a problem? I think I do. All right, let's do a, it turns out the problems with the Dirac delta function are simpler to solve than the problems with the unit step function. So let's, but what is the, I'll solve a more complicated problem. But what is the physical purpose of, why do we want to use the Dirac delta function? Well, suppose we have a spring mass system and we hit it with a hammer, okay? And we'll probably solve that problem tomorrow. If we have a spring mass system, we hit it with a hammer. Then we have a very short impulse. It turns out we could model that behavior with the Dirac delta function. Or if we have a circuit where suddenly there's a very fast voltage spike, okay, in the circuit, then we can model that with the Dirac delta function. So that so the Dirac delta function allows us to model problems where there's very short impulses to a system, and they occur a lot in nature. Like when you're hitting a golf ball, all right. If you're hitting a golf ball or a baseball, it's a very short impulse, and it's those type of problems that the Dirac delta function comes in handy. So let's see. I think I got time. Let me solve a simple problem with the Dirac delta function. I wasn't planning on going this far today, so this is great. We'll have more time to review. Okay, so now notice that, let's say we have a vibrational system. This is a simple problem that's in my notes. And this could be something where you're hitting something with 4 pounds for a very short period of time at 2 pi. Now, what's going on here is that, okay, well, let's just first solve this differential equation, then I'll talk about it. So, but at time t equals 0, nothing's happening. In other words, this thing is just sitting there, right? Until time equals 2 pi. So it's just sitting there. It's not moving. It's just sitting there until time is equal to 2 pi. And then at 2 pi, we hit it. And maybe this is a spring mass system. Maybe this is representing a spring mass system. We'll actually do that tomorrow. And we just hit it, okay? And then it's gonna start vibrating, right? So it's doing nothing until 2 pi, and then it starts doing something after 2 pi. So that's what we expect our solution to look like, all right? That's what our solution should look like. So, so let's see. So we take the Laplace transform of both sides. I'll take the 4 out. Okay. Now, remember, this is 0. So this is just going to be s squared big Y of s, right? And then this is just because these two are both, this is 0 too. By the way, I forgot that one of the initial conditions was 0 on problem number 4. There was a typing error. Didn't have the 0. Yeah, this was 0, and I think this was 1. Yeah. Okay. I think everybody knows what I'm talking about. All right. So now, then this is going to become 4. This will become 4e to the minus, right? When I take the, I'm just using the property of the Dirac delta function that we just learned about, how to, what the Laplace transform of this is. This is just going to be, okay, over s. Okay. So that's it. So this is a simple problem. So now I have to solve this. Okay. And okay. All right. So what is s squared minus 1? This is just, well, let me do this. Let me put the 4 out. Okay. So this thing here is just sine, right? I have a 1 here, right? This is k squared, and this is k, right? So this thing is sine. But now I got this e to the, I got this here too, right? So when I take the inverse Laplace transform of both sides, take the 4 out, inverse. Right? Okay, so this just becomes y at t, right? And I take the inverse, and this becomes 4. Now this is sine, right? This is sine. This is sine of t. However, the t is shifted, right? The c is shifted because I got this exponential. And I got to put something else down, right? I got to put down the unit step function. Don't forget the unit step function. Okay, so that's, let me check my notes. Okay. All right, so this is what's nice and neat in my notes, right? So, so this turns out, but I graphed this problem, right? So in other words, from 0 to 2 pi, it's doing nothing, right? It's not moving. And then we hit it, we give it the sharp impulse and it starts going. And because there's no dampening, this thing will go on forever, right? So tomorrow we'll do a more complicated problem with the Dirac delta function where we also have dampening. And I think we'll do a problem like that tomorrow. Let's see. Yeah, we'll do a problem like that tomorrow. And then we can also do an electric circuit problem. Okay, let's see. All right, does anyone have any questions on today? So the problems that become difficult is when you have a shift, you know, when you're applying more than one theorem at the same time, or more than one property at the same time. Like the problem that, let's see, where was it in my notes? Those seem to be the more difficult problems. Yeah, I'm talking about is a problem like this, right? Where you have to realize, and I tried to justify everything here, right? So these are like the most difficult problems where you end up having the, you know, the theorem we learned yesterday, and then applying the unit step function, right? That's going to cause a shift, and then this here gives us an exponential in front of it, right? Remember that this is giving us the exponential term. Like that's find it here. Yeah. Yeah. So for example, like this is what we did yesterday, right? Where we have you know, sine of 4t. This is what sine of 4t is. But then if I have yeah, the inverse of this, right? The inverse of this now, this is gonna this is the inverse. This is the Laplace transform. There's no I here. Good thing I looked at that. We're taking the Laplace transform here. What am I? Let's see. No, it's okay. I'm showing here that this is the Laplace transform of this, right? And this, when you take the Laplace transform of this, you get this. You take the Laplace transform of this, you get this. Okay. All right. But it's, yeah. I don't know why I got the minus ones there. There's no minus ones. Trying to see what maybe this is correct, right? This here we're taking the inverse. You get the inverse of t, but there should be no minus one here. Okay. All right. Any questions? I guess that's it for today. We got 5 more minutes, so I'll stay on if anybody has any questions. I hope you're finding the exam not too difficult, right? It's only 4 problems. So I'll see you all tomorrow. But I'll stay on if anybody has any questions.
Bye, Professor. Have a great day.
Okay, you too. But I'm not going to answer questions on the exam unless they're like, you know, I'm not going to help you do the exam. But yeah, you can ask questions. If you have something that maybe you can't read or something, you can ask questions about that.